Good morning. I'm Dr. Sanjay Jain, Associate Professor in Mathematics, SPC Government College Ajmer. Today we are starting a talk on Continuum Mechanics, your optional paper, in which we need some idea of vector and tensor initially. Most of the science students are already familiar with two type of tensors. Generally, we say we are already go through with the scalar and vector. A scalar or a quantity characterized by magnitude only is a tensor of zeroth order or called scalar, and a quantity characterized by magnitude and direction is a tensor of first order, or in general term first order tensor we say vector. These and other higher order tensor will be designated in the text by index notation. In continuum mechanics, we use the tensor in index notation. A scalar is indicated by a single base letter without suffixes, such as a scalar function phi. It has the same value at a given point in space regardless of the axis to which it may refer. It is in a sum all properties of scalars, and in case of vector of tensor order 1 is having magnitude and direction, which we studied in physics and many places. In your previous class, MSc previous class, you also go through with the tensors. Here we discuss vector and Cartesian tensor. What is a tensor? A tensor is an entity whose components obey certain basic transformation law when we transform one coordinate system to the other. If the coordinate system be Cartesian coordinate system, then the tensor be called Cartesian tensor. Or sometime in algebra sense, we have a tensor defined on a vector space with an orthonormal basis is also a tensor, Cartesian tensor. Here we use vector and Cartesian tensor. Yeah, in continuum mechanics, simple A, here we mention simple A tensor of zeroth order, because that simple A doesn't have any index. So it is a tensor of zeroth order, and that is known as scalar. AI, that having in a one index, that is I. So tensor of first order, this is called vector. Okay. Aij, this is called tensor of second order, and this is also known as matrices because its representation is look like a matrices. Aijk, tensor of order third or third order, and go on through Aijkl, that is tensor of order fourth, and so on. We got different kind of tensors or different order of tensors. Now, in introduction part, in Cartesian tensor, calculus will be used in the text in discussing the fundamental concept of continuum mechanics. It's very important part of continuum mechanics is one of that is Cartesian tensor, because whole derivations in continuum mechanics are based on the tensors notations and tensor basis. For those who are not familiar with use of Cartesian tensor, The remainder of the chapter is devoted to the basic definition. In the first chapter, we just discussing or studied about all definitions and all properties of tensors, of Cartesian tensors, and transformation law and fundamental mathematical operations, theorems of vector analysis, and advanced calculus will be studied in terms of the index notations of Cartesian tensor. It is not the intention of this chapter, however, to furnish detailed proof of the theorem which may be found in standard texts treating these subjects. So this is just of the introduction of the first chapter of vector and Cartesian tensor, an elementary idea and some new idea we have discussing and studied here. Yes, this is index notation of a vector. We have an idea of a vector is nothing but any vector of a bar. We have already written in earlier classes a1i plus a2j plus a3k. Here we consider Here we consider and introduce the well-known unit vector in continuum mechanics, the ijk, represented in red ink, is changed in continuum mechanics by E1, E2 and E3 notations. So when we having an idea of vector A is nothing but a1i plus a2j plus a3k should be changed in continuum mechanics is a1 e1, a2 e2 and a3 e3. This is a vector notation in continuum mechanics, ijk replacing by e1 e2 e3. This is the one change in continuum mechanics. Ijk changed to E1, E2, E3. E1, E2, E3 are unit vectors of axes. Okay, where A1, A2, A3 are the rectangular projection of the vector. Here you can see in the red line, this is an A vector, and vector component on the axis E1, E2, E3 are represented by the blue line, that is A1, E1, A2, E2 and A3, E3. These are the rectangular projections. That's why A can be written as rectangular projection of one axis, that is E1, rectangular projection on second axis, that is A2, E2, and similarly on third axis E3, E3. So A can represent by A1, E1 plus A2, E2 and A3, E3. Then we also going to, you are seeing that vector A drawing an angle theta 2 on the second axis. You are seeing here theta 2. And in coordinate geometry, we know that angle denoted by vector A make with the axis is known as direction cosines. Okay, so cos theta 1 is the direction cosine with axis 1. This is denoted by small a1. That is an important here. You always denoting the components by capital A1, capital A2 and capital A3. But the direction cosine represented by smalls. These are the two parallel lines of blue lines. You are seeing here A1, A2, A3. This is nothing but A1 is the direction cosine with respect to the first axis, that is noted by cos theta 1. A2 is the direction cosine cos theta 2 with the second axis. Similarly, A3 is the direction cosine with the third axis, that is cos theta 3. So A small a1, A2, A3 are the direction cosines which we use in the next slides. This is an important. Okay, so this is a simple representation of a vector as diagrammatic way. Yeah, we have taken a small part. Let this be A be the vector making an angle theta 1 and the component is A1. So in that case, if we draw a perpendicular with A to that axis, we get cos theta 1 by definition A1 upon A vector. Okay. When cross multiply, we get A1 is nothing but A cos theta. And in our earlier slide, what we see cos theta is nothing but small A1. Cos theta 1 is angle direction cosine, so it denoted by a1 is a1. Okay, so now we got here a1 is a1, similarly a2 is a2, similarly a3 is a3. By combining these three, we can directly say ai is nothing but a AI, that is general index notation. Okay. What other thing we are using here? When we squaring these and adding these. So this is nothing but that left hand side a1 square plus a2 square plus a3 square is nothing but a is common. So a square cos square theta 1 cos square theta 2 cos square theta 3. And we know by the cos identity cos square theta 1 plus cos square theta 2 plus cos square theta 3 is nothing but 1. So what we get a square is a1 square plus a2 square plus a3 square, and finally a is under root a1 square plus a2 square plus a3 square. This is using here again. So what we get ai is small ai. You are seeing in red ink. So AI is nothing but a capital AI upon capital A. So if we need A1, putting I equals to 1, so we get A1 is equals to capital A and 1 upon A. The value of A we know under root A1 square plus A2 square plus A3 square. So what we get direction cosine in terms of components A1, A2 and A3. So A1 is nothing but A capital A1 upon under root of value of A, that is A1 square plus A2 square plus A3 square. Similarly A2 is nothing but in numerator we get A2 upon under, in denominator the same value. Similarly in A3 nothing but A3 upon under root A1 square plus A2 square plus A3 square. So these are the formula for the vector and their component and for direction cosines, which are very useful when we using in the basis. So this is a simple idea of vector and Cartesian tensor and notations. So today we are doing till there only. Next in next lecture we are going when the direction cosines and ratios with two different axis system, how the point is changed. We are using in that notation. So in next lecture we are studying transformation law for a vector. Okay. So thank you.